Here is an experiment. Take our favorite coin and toss the coin repeatedly until two successive outcomes are the same. Until two successive tosses are the same. We could ask a question about such a conceptual experiment. What is the chance that by the time you terminate your succession of tosses, that you'll have tossed the coin 4 or more times? Now, here's an experiment you can actually do at home. Pause for a moment, try it out. See, without doing any analysis, whether you can come to an understanding of what the chances might be. Pause for a moment, think about the problem. Come back when you're ready. Okay, you're back. Now, our first step in this process is to try to come up with a mathematical description of the possible outcomes of this experiment. Now, before we write anything down, imagine what could happen. Well, the experiment is clearly going to take more than one toss of the coin, because you need two successive tosses to have the same result. The smallest number of tosses you could imagine would be 2. And if you were to terminate after 2 tosses, then it's manifestly clear that both tosses have to be heads or both tosses have to be tails. Excellent. We've got a starting point. We've identified 2 of the possible outcomes, heads and heads or tails and tails. What if you don't throw heads and heads or tails and tails? That means you must have had an alternating sequence of heads and tails, either a head and a tail or a tail and a head. If that is the case, you will toss the coin again. But now there's a possibility that you could repeat what you had thrown on the second throw. If that is the case, then you will stop on the third trial. Now a picture is emerging. So in the third trial, you could have a head, a tail, and you stop. Or a tail and a head, and you stop. If at the end of the third trial you haven't repeated a coin toss, you will toss it a 4th time. Now the picture is becoming apparent and the notation is becoming clear as well. So, for example, we could start writing out the possible outcomes of the experiment as follows. Head, head, tail, 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 head, 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 tail, tail, head, tail, head, head, tail, head, tail, tail, and so on. The dots at the end of the screen tell us that this experiment could, in principle, go on indefinitely. There is no fixed bound where the experiment ends. You cannot guarantee that the experiment will be done and dusted after 100 tosses of the coin, or after 1,000 tosses of the coin, or after 1,000,000 or 1,000,000 or any number whatsoever. In principle, albeit with an incredibly small chance, the experiment could go on forever. Now, for it to go on forever, it's clear what must happen. You must start out with an alternating sequence, and that alternating sequence should persist indefinitely. Surely we can conceive of this happening, though of course the chances should be very, very, very small that it go beyond even more than a few tosses. Okay, this is an example of a gedanken experiment. You notice that this experiment is never actually done. No one has ever tossed this game and seen all possible outcomes. There's an infinity of possible outcomes. But it can certainly be conceived of being done. And we can identify, in principle, the family of outcomes, of course, without listing all of them. But we describe it compactly. Things like start with a head, go with an alternating series, and then conclude with 2 of the same. Oh, this is nice. Start with a tail, go with an alternating series, and conclude with 2 of the same. How long is a series? Any fixed integer. Now we have a way of describing it, visualizing it, even though, of course, we have no earthly hope of writing down all possibilities. There's an infinity of them. This is so far so good. it gets a little trickier to ascribe an idea of chance. Now, so let me throw out some numbers at you and see if I can defend numbers as measures of chance for each of these outcomes. I claim that the numbers I've given you in the second row of the table are actually appropriate for the problem at hand. Now, how would we go about justifying something like this? Well, an argument might go as follows. Let's start by looking at those trials where the experiment concludes after 2 tosses. If that is the case, you must have either thrown 2 heads or 2 tails. Now, of all possibilities for 2 tosses, well, how many are there? Well, there are exactly 4 possibilities. Heads, 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 tails, tails, heads, and tails, tails. You have 4 possibilities, and naturally enough, because we think our coin is fair, we imagine that these 4 possibilities for 2 tosses are equally likely. If that is the case, then the chance of seeing a head-head in 2 tosses should be 1 in 4. And likewise, by an entirely similar argument, the chance of seeing a tail-tail in 2 tosses should again be 1 in 4. Suppose the experiment doesn't stop after 2 tosses, but it moves on to 3 tosses. How many possibilities for 3 tosses are there? Now, there are 8, or better, 2 to the power 3 possibilities. 2 times 2 times 2 for each of the 3 tosses. What are they? Well, we can very lexicographically write down the possibilities if we wished, and you might want to do that. Head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. There are 8 possibilities, and again, we have no reason to believe that any one of them is any more likely than any of the others. We assign to each of them equal chance. Out of those 8 possibilities, the chance of getting, for example, a tail, head, head, well, that's 1 out of the 8 equally likely possibilities, and therefore you assign a chance of 1 in 8 to tails, heads, heads. And likewise, a chance of 1 in 8 for head, tail, tail. And we proceed apace. If you look at 4 tosses, there are 2 to the power 4 or 16 possibilities. I will not weary you by telling you what they are, though you might want to write them down just to make sure that your intuition is now solid. Of those 16 possibilities, each of the 2 possibilities where you terminate is 1 of 16, and therefore you assign a 1 in 16 chance. And now you see that these chances are decreasing like 1 in a power of 2. Here now is a measure of chance for the elementary outcomes in an experiment which has a countable infinity of possible outcomes. Now, you might look at this and say, well, gee, this is all very specious and hand-waving, but how do I know that the chance you assign to, let's say, a termination in 50 tosses, in other words, 1 in 2 to the power 50, is right? What if you're wrong? The short answer to that, of course, is that the outcomes which require 50 tosses have not been fairly tested. Let's say, for example, you look at 50 tosses, or even say 60 tosses. The chance of an experiment requiring 60 or more tosses is, in this model, 1 in 2 to the 60. Now, 2 to the 60 is a mind-bogglingly large number. It's about 10 to the power 18. It's about the lifetime of the universe since the Big Bang. Even if we tossed a coin once every second for the entire lifetime of the observed universe, we would not have exhausted those possibilities. So we could legitimately say that I'm giving you a number and disprove it if you can. It surely has not been fairly tested. Of course, these numbers are getting fantastically small. The second part of the justification would be very simply that in the range of termination with a modest number of tosses, let's say 5 or 6 or 7, the numbers we put down fit wonderfully well with observed experimentation. and therefore we have no reason to believe that our logic is unsound, and so we extrapolate onto an infinite sequence. Okay, with this for justification, we now have an experiment with an accountable infinity of possible chance outcomes, and we have, in a systematic, principled manner, assigned certainly unequal probabilities, chances to each of these outcomes. Now let's look at what the event at hand is. That your experiment required you to toss the coin 4 or more times. Recall, our experience has told us that events may be identified with subpopulations, aggregates of possible outcomes. What are the outcomes here that are appropriate to this event? Well, clearly enough, all those sequences which terminate in either 2 heads or 2 tails, which start with 4 or more members in the sequence. Things which are identified in the green band stretching out infinitely to your right. And we can capture that entire infinite green band by a simple compact notation. Let's say greater than or equal to 4 tosses. And that succinct description captures that entire infinity. And now we want to figure out what is the natural measure of chance for this event. And we appeal immediately to the fundamental principle of additivity. The whole is equal to the sum of the individual parts. The probability of the event that you need 4 or more tosses is the probability of the event that you needed precisely the sequence heads, tails, heads, heads, or the sequence tails, heads, tails, tails, or and so on. And we now decompose this event into an infinite number of shards or pieces, and we simply add the probabilities. Bingo. Pause and write this down. We've decomposed the event greater than or equal to 4 tosses into a sum of individual probabilities. But now we've extended our finite intuition to a countable infinite intuition. But the logic appears clear. This appears to be completely unexceptionable. We believe it, we write it down, appealing to a global principle of additivity. And now, since we've got numbers we've assigned to these raw chances, we very simply plug in, and I've grouped these numbers pairwise, 2 at a time, because by looking at our table above, we see that each of these probabilities appears in pairs. There are 2 1 in 16ths, 2 1 in 32s, 2 1 in 64, and so forth. Factor out a 2 and then add up the remaining probabilities. You'll notice that each of the terms inside the round brackets has got a factor 1 in 16 that is common to it. Naturally enough, as long experience has taught us, we factor out the term 1 in 16. And what remains inside the brackets is a sum of reciprocal powers of 2. Oh, we are very familiar with this. This is what, in a first calculus class, we call a geometric series. And the geometric series identity tells us that geometric series with parameter 1/2 sums to the reciprocal of 1 minus 1/2. We do the arithmetic, and we find the chance of needing 4 or more tosses in this experiment is now 1 in 4. Did your guess come close to this? Go back and think about what you did to come up with a guess, and now look at the analysis and see what went wrong or what went right.